Broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to the weeks 3 to 4 S2S webinar series. My name is Karen Keith. Before we get started, just want to let everybody know that you will be in listen only mode. And if you have any questions for either of our presenters, we want you to ask them in a Google document. I will be posting the link in the chat throughout the presentations today. And so please go there and ask your questions and we'll go through them if we have time with the presenters. If not, they can respond after the webinar. We have a VLab page with all of the information for this webinar series. So to register for upcoming webinars, we have the links here. I'll be posting the one for October, probably later this week. If you want to subscribe to any notifications, you can fill out a Google form here. And if you are interested in presenting at one of our monthly webinars, please fill out our Google form. We have some openings starting in 2022. I think January and March we have some openings. So if you have something you'd like to present, please fill it out and we can work it into our schedule. With that, I'm going to pass it over to our first speaker today.
Good afternoon. Shall I start?
Yes, please. Thank you.
Full screen mode.
Looks good.
Okay. So yeah, thanks for the opportunity to report our recent progress in developing CS predictions with a UFS-based system. This is team effort with 6 team members. As you can see, 6 names here. Before I start, I want to acknowledge OSTI support and EMC Dynamics and the couple model modeling group for their hard work and successful progress and for making available of the model to us. And also I want to thank Jim Petresco and Rick Tolman for their feedback on the development of CS products. All right. Okay. So I would like to start with some challenges in CS predictions from inside operational CFS. And then I will talk about a little bit about the current CPC experimental CS prediction system. And I will spend most of the time to report our recent progress in upgrading the system to UFS-based predictions. So about CFS. So everybody knows CFS. It was implemented in 2011. One one particular thing in this model is it is one of the first couple models for seasonal and subseasonal predictions that includes an interactive dynamic CS component. So we were excited at that time to develop CS prediction outlooks based on CFS. And then we quickly realized that the CS predictions from CFS are not very useful. There are two major issues. One is the model. Now, CFS has excessive solar radiation, downward solar radiation at the surface. And another problem is initial condition. CS thickness initial condition from CFSR are too, the thickness is too large compared to other analysis estimate. So with these two big issues, seasonal predictions from CFS have much weaker seasonal cycle, and internal anomalies also contains large errors. So because of that, we configured another system, which we call CFS M5. This is very similar to CFS, except that we used a newer GFS version, which is 2015 version for atmosphere. And for the ocean, we use M5 instead of M4 that it was used in CFS. And for initial conditions, we still take CFSR for atmosphere. Ocean is also CFSR. The big difference is CIS. We use CPC CS initialization system produced CS thickness, which is much more realistic compared to CFSR CS thickness. And with this system, we produced two types of predictions. One is seasonal, which was produced every month from each conditions on 21st to 25th, and the target period is 9 months. And another one is week 3-4. This is produced weekly from Sunday. It covers 6 target weeks. These predictions are regularly used by NWS Alaska to provide guidance to their stakeholders and by Alaska Center for Climate Assessment and Policy in Alaska Region Climate Outlooks. So just want to give you a quick assessment of CFS M5. So this is a weekly CS prediction anomaly correlation scale of CS extent. So this is based on 2012 to 2018. Each box is for one initial month. I only presented, no, sorry, these are all months. That's what I only presented about season. Anyway, these are for all months. We don't need to look at all individual month because the comparison is the same for all months. So basically, okay, we have two curves. One is blue, which is from the new CFS M5. The other is yellow from operational CFS. Obviously, the correlation scale from CFS M5, the system we reconfigured, has higher scale for all individual months and for all 6 target weeks. So that's for weekly. And for seasonal, we compared the scale for 3-year real-time period from 2015 to 2018. We used another metric for the comparison, which is Haddock scale score for Arctic CS existence. So basically, this measures local comparison of sea ice rather than a one total number for the entire globe. So the left panel is the scale from CFS, operational CFS, And the right panel is Cfs M5. And the x-axis is initial month, and the y-axis is target month. So one major feature is for the summer season, the target summer season, say July, August, September. All forecasts have a negative scale. So this was a big problem because that is an important season. And looking at the CFS M5 forecast, the scale is significantly improved. So that's improvement. However, we also see for target winter season, like December, January, the CFS M5 the scale is even lower. It's more than negative. So this is something we want to improve with the new system. So then, with the availability of the UFS, we started testing the system, and we hope this will become an even better system for CS prediction. The model we use is a unified forecast system, prototype 5, UFS P5. Again, thanks to EMC Dynamics and Couple Modeling Group for making the model available to us. The model has 3 major components. Atmosphere is F33 version 15. We run this at the resolution of C96, and ocean is MOM6, CS is size 6. So we first test the default configuration and see if there's any bias that need to be adjusted. And we did find there's a large CS coverage bias in the prediction. So the upper right 2 panels compares CS concentration between CDR, which is observation, and UFS forecast for September, initialized from June 1st. So this 3-month lead forecast. The major issue is, as we see, is the large negative bias in Central Arctic. So CS is essentially missing there for a large part of this area. So we look at the other variables, and we believe this was due to the large positive downward solar radiation bias near the surface, as indicated in the lower panel, which shows the solar radiation bias. We see that this is for June, which is during the period of CS melting. So surrounding Arctic, we see positive solar radiation. That caused the too strong melt of the sea ice. So that was the cause for the large CS coverage bias in later months. So with this bias and with our earlier experience, we test the 3 cloud radiation cloud parameters, and one sea ice freezing temperature parameter. So we carried out 23 experiments for cloud parameters, just to see if there's an optimal setting for CS prediction. Without showing all details of this 23 experiments, I just list the final selection here for these 3 parameters, cloud parameters. Cloud water radius for autoconversion, and ceasing over ocean, and cloud water to rank conversion efficiency. And in addition, we also tested the two options for ocean water freezing temperature, and as also found by the EMC group, using a constant freezing temperature improves the CS prediction. So we use that option. So we use this final selection of the parameters and we carry out okay, sorry, before the handcast, I just want to show you the comparison, the impact of these parameters. So left panel compares CS concentration for the same target month, September 2015. So upper two panels are observation and this forecast based on control configuration, and the lower left is the simulation with our final selection of the parameter values. We see a significant improvement. This is just one single run, so there's still an open area in the central Arctic. We consider that's probably just like a sampling issue. Anyway, we see a significant improvement, so we decided to use this setting. The right two panels compare the downward solar radiation. We see a slight decrease in downward solar radiation. We don't want the significant change to the to this quantity. So we see consistent with the change to the parameter values, we see a reduced downward solar radiation, and that improves CS prediction. So this is our final selection of the parameters. So with this configuration, we carry out handcasts using, we still call this UFS P5, even though the parameter values are adjusted. So we carry out 45-day run for weekly outlook for historical period 2012 to 2020. We produce 4 forecast members initialized each day from melt season, April to September. So this has been completed. And another set is 9-month runs for season outlook. This is for handcast period 2007 to 2020, 14 years. And we produce 1 forecast runs initialized each day from 21st to 25th. This is also mainly for target season, melt season, target melt season. We initialize the runs from March to August. So this is also completed. And for evaluation, we compare mean CS concentration and CS extent and Haddock scale score for CS existence. So CS existence is defined when CS concentration is equal or greater than 15%. We also compare individual models with multi-model ensemble. So first we look at the 45-day handcast. Here we just compare one particular target week 4, CS concentration bias. So I have 4 panels here. Upper left is UFS. Upper right is Cfs M5. Lower left is CFS version 2, and then lower right is a multi-model ensemble based on all these 3 models. So clearly, UFS and CFS M5 files have very similar pattern. Amplitude is also comparable. And CFS version 2, lower left, shows more positive bias and slightly larger amplitude. And the multi-model ensemble is interesting. Looks like the multi-model ensemble reduced the bias substantially compared to all individual models. So that's something useful. And so for skill assessment, we look at the Haddock scale score. We have 6 panels here. Each panel is for 1 initial month. So the contrast again is similar. So we focus only on 1 month, say upper left or April. We have 6 target weeks from week 1 to week 6. I have 5 curves here. The blue is UFS, and the orange is CFS M5. Green is CFS version 2. Black is persistence the forecast based on persistency. So this is just for reference. And the purple one is multimodal ensemble, MME. First, we see that UFS and the Cfs M5 are very close, they're very similar. And green, which is CFS, is lower. We see a well separation between CFS M5, UFS, and CFS version 2. So this contrast is the same for all months except for September, which shows that UFS is actually slightly better for the first 2 weeks. So the multimodal ensemble is actually higher for all months, although the difference is tiny for most of the months. But it may be a useful option for weekly forecast. So for seasonal, I have first I look at the climatology. We look at climatology. Here is September CS extent from April, so it's 5 months lead time, or maybe 4 months lead time. The left panel is for September, and we see that green curve is UFS, red is CFS M5, and blue is CFS version 2. So CFS M5 and the UFS are both show some errors compared to observation, which is black. Amplitude is quite similar, and both systems produce closer CS extent compared to CFS version 2, which is too large. Yeah, see the blue curve. More interesting results are for January. So red panel is August forecast. No, sorry. Yeah, the January forecast from August. Two major biases in the CFS and the CFS M5 are the too slow advancement in Bering Sea, southward advancement, as we see in the red curve and the blue curve. And this is significantly improved, with green, which is UFS. So that's a big improvement. And another bias is in Atlantic. Both CFS M5 and the CFS version 2 produced too much CS. And UFS improved that. So that's also very good. So for internal times anomaly scale, we calculate Hadley scale score similar to the earlier evaluation. So here I have 5 panels. Upper left is CFS version 2, and upper middle is CFS M5, and upper right is UFS. Again, the x-axis is initial month, and the vertical axis is target month. This is for different years, so you can see the comparison between CFS and the CFS M5 look different. So this is for 14-year comparison. Again, CFS M5 improved summer season. That will remain the same. However, the winter season is worse. That's something we want to improve. And fortunately, the new version and new model UFS improved the scale for all seasons, summer and winter. So that's a very good progress. And the lower 2 panels are multimodal ensemble, and lower left is all 3 models, and the second and left is UFS and CFS M5 only. We are hoping the two models of multimodal ensemble may be better than all 3 models. But what's interesting is actually UFS is better than multimodal ensemble, no matter what option to use. So that's also another interesting result.
Wanqiu, we'll need to wrap up in the next minute or two, please.
Yeah, okay, I will skip this, I skip this. This is for one individual case. Just want to let you know that individual case, it's also improved. So in summary, we see a significant improvement in week 3-4 CS prediction with current CFS M5 compared to our version of CFS version 2. And CFS M5 improved the seasonal forecast for summer season, but not for winter season. And UFS maintain comparable scale with CFS M5 for week 1 to week 6, and both CFS and the CFS M5 produce improved forecasts compared to CFS. And for seasonal, the new model improved all target seasons, so that's a very good progress. And multimodal ensemble is a good choice for week 3-4, but does not to be so for seasonal. So that's what I have. Thank you.
Great, thank you. There is a question in the question document. If you could go over there and type your answer, since we don't have time to go over it, that'd be great. Anyone else has more questions, you can go ahead and ask them in there as well, and Wanqiu can answer them there.
Okay, CS niche condition, actually,
sorry,
yeah.
can you just type the answer? We need to move on to Cory.
Okay.
Great. Karen, can you confirm that you can hear me and see my screen?
Yes, it looks great.
Okay, great. Thank you. Thank you, Wanqiu, for the very nice presentation. Again, my name is Cory Baggett. I'm a contractor who provides the scientific support to the Climate Prediction Center. The title of my talk today is Evaluating the Potential of a Blocking Predictor in a Hybridized Dynamical-statistical Model for Improved Week 3-4 Temperature and Precipitation Outlooks. That's a mouthful. Probably a shorter way of saying it is, can we use atmospheric blocking to improve our Week 3-4 outlooks? I want to give a shout out to my colleagues at CPC who have provided enormous assistance and support over the past year on this project. This project is a fiscal year 21 milestone that has received support, supervision, and funding from OSTI. So thank you to that. This has been a very fun project to work on. And thank you also to NOAA, WPO, and WSS2I for this opportunity to present today. So moving on to the presentation here, why do we care about blocking? So maybe just a brief overview would be helpful. So what I have here is a map of anomalous C500 anomalies that is present during blocking at 300 East during December through February. So what's striking about this map is you see these positive height anomalies to the north, negative height anomalies to the south, and the amplification is so much that the meridional height gradient actually reverses, such that you no longer have westerlies in between those two anomalies. They actually reverse to easterlies. So that's where the word blocking comes from. The westerlies, the climatological westerlies, are blocked. So this blocking obviously comes in the form of large-scale stationary waves. They can divert the storm track. This particular blocking at 300 East is very reminiscent of the negative phase of the North Atlantic Oscillation. And I should mention that what I used to calculate this blocking was a particular method developed by Tubaldi and Molteni in 1990. There are many different ways of calculating blocking out there in the literature. Barnes et al. 2012 details quite a few of them. But in this case, you know, we'll try many of them, and we'll actually explain what we end up using as we go forward. So again, you know, blocking can occur at different longitudes. Here's an example over the North Pacific where you have blocking, you know, diverting the storm track over the Pacific Basin. So why is this blocking important? Why is it relevant to week 3-4? Well, blocking is known to persist for several weeks at a time. And one can imagine if the atmospheric pattern stuck for several weeks at a time, it can have very profound impacts on surface weather, such as temperature and precipitation, if that blocking is occurring nearby. So for example, blocking has been linked to extensive drought in the West. It can divert atmospheric rivers into Alaska. They're really known for extreme cold conditions across CONUS and Europe at times as well. But you know, we're focusing on CONUS for this presentation. One can think back, if one's memory is long enough, back to the late 1970s when blocking was very profound and led to extreme cold in the East. 2009, 2010, for those of us who are younger, when the NOAA was very negative almost the entire winter long. And we've seen episodes since then as well. Blocking is also very much related to sudden stratospheric warmings. Blocking can occur both before and after sudden stratospheric warmings. It's a very interesting relationship between the two, but they certainly have an impact on that. So blocking, they have this very important impact on surface weather. It's important to understand those impacts, and maybe we can actually get some enhanced predictive skill by knowing when blocking is going to occur or when it is occurring. So how often does blocking occur? Well, it turns out not too often. So these are frequency maps of blocking frequency as a function of season on the y-axis and the longitude where the blocking occurs on the x-axis. I have two different plots here, one for the Tebaldi-Molteni index and one for the Barnes 2012 index. And really the only difference between these two indices in their calculation is that Tebaldi and Molteni use a fixed latitude to calculate blocking, whereas Barnes and al. 2012, they allow that latitude to vary with longitude as to where the storm track actually exists. So anyway, both indices are pretty similar over the North Atlantic where blocking frequencies peak. And generally speaking, that peak frequency is about once in every 7 days or so. But of course, this is over, 79 through 20 period, so that blocking actually occurs in many days in a row, typically in a given season. In many seasons, you don't have any blocking at all. But the blocking indices actually have quite a bit of difference over the Pacific Basin, as you can see, where particularly like over the date line where they're complementary to each other. So this kind of raises the question, if we're going to use blocking as a predictor, which index do we use? Which longitude of blocking are we most interested in? Which index, which longitude has the greatest impact on week 3-4 temperature and precipitation? So we tried many of these indices, and it turns out we eventually went with something that was much simpler, just using the NAO for Atlantic blocking and the PNA for Pacific blocking. And I kind of put that in quotation marks because the NAO itself is not blocking, although when you look at the negative NAO, it's highly correlated to when blocking occurs. Similarly for the Pacific North American pattern, it has been related to upstream blocking as well, but it's not technically blocking. So forgive me if I use the words a little interchangeably here, blocking, NAO, PNA, but that's where we're going with the forthcoming results. So how are we going to inject blocking into CPC's forecasting process? So maybe a brief overview would be helpful here. So this is the forecast that we issued for week 3-4 just this past Friday, temperature on the left, precipitation on the right. And we issue a very simple forecast, 2-category probabilistic forecast of above or below normal temperature and precipitation. And you can see this forecast valid period is beginning September 25th, and it's for that 2-week period. And generally for this forecast, we're predicting above normal across much of CONUS and Alaska. And that is, you'll see this forecast quite often where below normal is not on the map, but you will see it sneak in there every now and then. And it's a difficult forecast to make below normal because you're working against the trend. So we need all the guidance we can get to forecast below normal, and maybe where blocking can actually offer some insight into that. So what tools does the forecaster use? Forecaster sits down and makes a forecast every Friday. It's a different forecaster each week. First starts off with the dynamical models, such as the JEFs, the ECMWF, the CFS, the Canadian, the JMA, models participating in the sub-X experiment. Another set of models that the forecaster will look at are statistical models, such as the multiple linear regression model, phase model, constructed analog, and a really neat model that's come on recently, the linear inverse model. So I've highlighted here the multiple linear regression model because that's what I'll be focusing on improving with blocking over the course of this presentation. And one might ask, why statistical models? Well, it's pretty well known with really rather recent studies that the dynamical models are deficient at forecasting blocking, not only for their onset, but also for their duration and for when they decay. So they have trouble with that. It's probably somewhat related to how well the models actually simulate troposphere, stratosphere interactions, because blocking is also related to that. So there are deficiencies. So we're thinking, maybe there's some hope with the statistical model. So that's what we're shooting for with this project. And for completeness sake, the forecaster also looks at equal weighted manual blends and auto blends. And I should mention that these blends do include the statistical models along with the dynamical models. So they do get put in there. And finally, intuition and consistency. This is where the human element somewhat gets involved, where you have peer input, you look at recent model errors, persistent soil moistures, anything that a map isn't showing you right on the screens, things that the forecaster should know and hopefully can spot before the forecast is issued. So you put all that together, you get your forecast. Like I said, they're issued once per week. Currently, the temperature outlooks are operational. However, the precipitation outlooks are still experimental due to a lack of skill. Precipitation is so tough to get right. So what is CPC's multiple linear regression model? And in shorthand, I'll just be calling that the original MLR. It's the control in this experiment. Can we improve upon the original MLR? So as a schematic here, I just want to show how this MLR is set up. So you have two periods, right? A training period and a verification period. So this particular schematic represents the training period. We have several predictors that go into this blue box, the model, the original MLR. We have a past predictor for ENSO 3.4. So what was ENSO 3.4 over the last 2 weeks? That's a value. What's the MGO look like when the forecast is issued? So the RMN indices on day 0. And what does the trend look like on day 0? So those are predictors you have in front of you that go into this training period. And then you also have in the training period the observed week 3-4 temperature and precipitation. So you throw all that information into the model, you develop your regression coefficients and equations, and you have your model that can be verified in the verification period. And before I move on to that next slide, I just want to point out and give special thanks to Daniel Harnos for developing this model. It's simple in its intent, but it's used every week, and it's such a valuable tool. And all I'm trying to do here is actually build upon it a little bit. So we'll see if we can make that happen. So moving on to the verification slide here, obviously in the verification period, we still know what ENSO was in the 2 weeks prior. We know our current predictors of MGO and trend, and now we're forecasting for week 3-4 based on the regression coefficients we developed in the training period. So what do those regression coefficients look like? So that's what I plotted here. Each row is the regression coefficient between a particular predictor and the predicand at a given week period, 2 week period. So week 1, week 2, week 2, 3, and week 3, 4 are the rows. And the columns are the predictors, the trend, the 2 RMM indices, and ENSO 3.4. And really what I want to point out here is that if you look at the trend, it's constant throughout all 3 periods, which is to be expected. The trend is simply an index that changes each year, so you're not going to expect that to change over that 4-week period. The 2MM, I'll move on to ENSO real quick here. ENSO, it's also a rather constant picture when you look at its regression coefficients. That's also to be expected. It's a seasonal signal that imprints onto the longer term trend. So one way of reading this is, the units for these plots are Kelvin per index. So when El Nino is in its positive, this is a positive state, El Nino. So when the index is positive, one can expect above normal temperatures in the north and below normal temperatures in the south. Now MGO is a bit of a different critter because it has a subseasonal component to it. So its signal as it propagates around the equator and its teleconnection propagates into the mid latitudes will change with lead time. And you can see that going from week 1 to through week 4, where in fact the warm signal in the east converts to a cold signal in the east over that time period, and a little bit different story for RMM2. But in essence, all of these predictors still yield a relatively strong signal towards week 3-4, and that's why Dan had set them up as using them as predictors in the multiple linear regression model. So what does this model look like when a forecaster sits down to use it? So this is an actual screenshot of the page, the forecast tool. And there's 3 components that go into the final forecast of the MLR. So in the top left, we have the MLR ENSO component. Then we have the MLR MGO component and the MLR trend component. And it turns out for this past Friday, the 2 components related with ENSO and the MGO are really weak. In fact, since ENSO is only a very negative value, there's really no signal coming from ENSO across CONUS and Alaska. MGO did have a component that was relatively strong and amplified in RMM2, but the teleconnection is not that strong this time of year, so there wasn't much signal coming from the MGO. And finally, the one that did have a signal was clearly the trend, where you see these above normal signals across the periphery of CONUS and of course over Alaska. You add them all up together, you get this bottom plot. So this was interesting actually this past week, because the statistical models actually very confident about warm across Alaska, but a lot of the dynamical models were actually forecasting cold, such as the Eastern WF. But if you remember the forecast I just showed that we put out, we favored warmth across Alaska. So you can see where the statistical model actually gets kind of thrust into the forecaster's thinking process, and we do lean to it from time to time. So the question is, can we improve upon this model, this original MLR, by adding another predictor related to blocking? So we're going to try adding the NAO as a predictor and call that the MLR NAO. So how well does the MLR NAO perform compared to the original MLR? So we'll adjust the schematic here now, and in the blue box, instead of being the original MLR, now we have the MLR NAO. We have the same predictors as the original MLR, but now in the training period, we've added this observed day 14 NAO. So the NAO 14 days in the future, and I'll explain why about this day 14 over the coming slides. And of course, we still have our observed week 3-4 temperature precipitation. We develop our coefficients from this training period and we apply them to the verification period. Of course, in the verification period, we no longer have the observed NAO at day 14. So what do we do instead? We're going to use a dynamical models forecast to the NAO. We're going to use the Jeff's forecast from day 14. Plug that into the regression coefficients and equations that we derive from the training period and get a forecast for week 3-4. So that's the MLR NAO in a nutshell. Maybe a little more explanation of day 14 is worthwhile over the next few slides here. So when you look at the regression coefficients associated with the NAO and subsequent temperature over the next few weeks, I wanted to start out here on this left column when I use the NAO from day 0 as opposed to day 14. And what I want to show in this column here is these regression coefficients, the amplitude clearly declines by the time you get to week 3-4 compared to week 1-2. In fact, most of the signal week 3-4 probably is coming from week 3, meaning there's really not much signal left at all towards week 4. So the time scale of the NAO teleconnection for surface impacts decays over a 2-3 week period, where we did not see that as to be as much the case with ENSO and the MJO. So the motivation for using the day 14 NAO is clearly that if we know the NAO at the beginning of the week 3-4 period, then maybe we have a better idea of the surface impacts that the NAO will produce in that week 3-4 period. So when you develop the regression coefficients using the day 14 NAO instead of day 0, you can see that that signal from week 1-2 shifts to week 3-4. And now we have a pretty strong signal at week 3-4. Of course, the catch is, how well do we know the day 14 NAO? How well is the model predicting it? So to get some insight onto that question, this plot was made, which is the correlation of the observed NAO versus the NAO from the model, the Jeff's model. And what he's plotted is the correlation as a function of season and lead time for the NAO prediction on the x-axis. And the main story I want to point out here is that the NAO skill, the correlation skill, actually exceeds 0.5 out to day 14 and when you average across all seasons in this particular model, which is not bad. So the model does a decent job of predicting the NAO at extended leads. But really, probably the best thing to do, rather than just looking at how well the model predicts it and how well the signal lasts, is really just go ahead and test all the different lead times, days 1 through days 15 of the NAO prediction predicted by the Jeff's model. So that's what we do with this plot. And these are, what's plotted is the skill score difference between the MLR NAO and the original MLR. So just subtraction of the two. And a different model is run or trained based on the lead time of that NAO predictor being from day 1 through day 15. And all these different models were tested as a function of season and that lead time. And what I want to point out is that the skill score difference actually increases as you increase the lead of your NAO predictor. So that was a good result in the sense that using that forecasted predictor, the NAO, actually adds value to the original MLR. And it seemed if you were to average across all seasons, we actually found that day 14 was where that value peaked, where that difference in skill score is the greatest. However, that clearly wasn't the case for the summer and fall months, where one could make the argument that you should be using an NAO predictor at shorter leads based on this plot. But for now, for this presentation, we'll be focusing on November through April in the coming slides. So we'll stick with this day 14 value. So far, these are just a summary of skill scores, but you can look at these skill scores on spatial plots as well. So a little explanation here, because I'll be showing several of these plots going forward. So these are, on the top left is the spatial skill scores of the original MLR. The second plot is the MLR NAO, and the bottom one is the difference between the two. So what is being scored here is temperature, and these are for forecast issuances over 2011 through 2021 from November through April. So all starts during November through April for that time period on Tuesdays and Fridays, so twice per week. And that will give you an N of 531 forecast samples in this case. So when we skill the original MLR, actually, let me point out these statistics. So on each panel, we have the HSS for CONUS and Alaska combined, the CONUS for HSS, and the CONUS for Alaska in each panel. And what happened here when we did this is original MLR scores for these forecasts an 11.7 over CONUS Alaska. But when you add the NAO as a predictor, the day 14 NAO as a predictor, it scores a 14.5, which is an improvement of 24%. However, when you actually look at the difference between the two, it becomes very clear right away that the skill score improvement is coming from CONUS, with the exception of the upper Midwest, while we have a decrease in skill over Alaska. In fact, skill scores over CONUS improved by 42%, which was, it's a pretty substantial number. So the question now becomes is how do we improve Alaska, right? Maybe we have something that works for CONUS, but is there a way to improve Alaska? So I'm sure most of you are thinking the PNA, okay, he's already mentioned that. So how well does the MLR PNA perform compared to the original MLRs? So we'll give that a shot now and show some similar plots as I've just shown. So the schematic here changes just slightly. Now, instead of having an MLR NAO as our model, we have an MLR PNA, and we're going to use that for Alaska. In the training period, we're going to use the observed day plus 12 PNA and justify it in similar ways as we did for the NAO. And in the verification period, we're going to use the modeled PNA from the JEFs at day 12 and get our forecast and verify it and compare it to the original MLR. So looking at the regression coefficients again, if one were to have used the day 0 PNAs instead of the day 12, then we could look at this left column and see that, again, that these regression coefficients fade as you move forward in lead time. So the skill or the signal of the PNA fades across CONUS, and also interestingly fades across northern Alaska on the North Slope. If you use the day 12 PNA, you can see now that the skill score is much more strong and increased over on week 3-4, and it's very comparable to the week 1-2 signal. So if the model is predicting the day 12 PNA well, we have a signal that we can latch onto with our statistical model if we're using that day 12 PNA in it. So how well does the model forecast the PNA? Pretty well. In fact, maybe a little bit better than the NAO. If you look at these correlations between the observed PNA and the modeled PNA as a function of season and lead time for that PNA, again, skill scores exceed 0.5 in terms of correlations out to day 14, so not too shabby. And those skill scores are peak through the winter and spring seasons, as we saw earlier with the NAO. So if you look at the difference in skill scores between the MLR PNA and the original MLR as a function of season and lead time of that PNA predictor, so you test all these different lead times, what we found here, and maybe it's not apparent because of the color scheme, but we actually had a peak in skill score improvement at day 12 across all seasons. So that's what we went with in terms of a predictor for the PNA. It's using its day 12 value. But definitely overall, this picture is not as exciting as the NAO. There was much more orange on the NAO map compared to this one, but we are getting something out of the PNA. So it's worthwhile looking at it on spatial skill maps as well. So similar to the NAO one here, where we have original MLR on the top left, and you can see its skill is 11.7 just as before. But now we have the MLR PNA model used to forecast for both Alaska and CONUS, and its skill score improves to 13.1, which is around 11%, not as much improvement as the MLR NAO. However, again, as if you look at the difference plot here, while CONUS scores really didn't change much, it's kind of a mixed bag, you can see there's substantial improvement in skill score across Alaska. So that was great. We have something complementary to the MLR NAO. We could use the MLR NAO for CONUS and the MLR PNA for Alaska. So how do we go about doing that? We create what's called a merged MLR. So like I said, we use the MLR NAO for CONUS and the MLR PNA for Alaska. So what do those plots look like on a spatial sense? Again, the original MLR on the top left, and now the merged MLR. So in this particular plot, any grid point in CONUS was developed from the MLR NAO, its forecast, and the forecast for Alaska were developed from the MLR PNA. And now we have a skill score improvement 11.7 to 16.8, which is a 44% improvement in skill score. And in fact, if you look at the spatial difference map, skill score improvements pretty much everywhere, although we still have issues improving over the Midwest, which is because the MLR NAO doesn't do well in that region, and then this merged model doesn't either, obviously. So it's a statistical model. Maybe this is some evidence of a one-size-fits-all does not work. Certain teleconnections and climate indices work better in some regions than others. And I think a demarcation between Alaska and CONUS makes sense in terms of the physical processes that may be occurring close to home for either of them. So, a question may come up now. Okay, so you're running this model regardless of what the actual amplitude of the NAO or PNA is, all right, or are. So you're running these forecasts no matter what those amplitudes are, and maybe you're just, not actually capturing a signal you want to capture. Maybe they're a forecast of opportunity. It stands to reason if the NAO is amplified, be it positive or negative, then one could expect a greater signal from this merged MLR and perhaps improve scores. So do we see that? So that's what this is doing now on this plot. Original MLR on the top left, and you notice the skill score has changed here. It's 12.9 instead of 11.7. And that's because we only have 176 forecasts now. So it turns out 176 of those 500 something forecasts were initialized when the NAO on day 0 was in an amplified state, be it positive or negative amplification. So why day 0? Well, we can observe the amplification of the NAO on day 0. We know what it's doing. One could ask, why not day 14? Well, we could have surmise, we could use the Jeffs to hope that it's amplified at day 14, but at day 0, we actually know. And some recent studies have shown that there is, when you have that known factor in front of you, the NAO being amplified, there is some enhanced skill going down the road of what the NAO will be. So in this case, the original MLR, as I said, was 12.9, but now when we only look at forecast initializations when that NAO is amplified, our skill score jumps to 23.4 in this merged MLR, a difference of 10.6, which is an 82% improvement over the original MLR when we throw in these blocking predictors to this model. You can see in the spatial difference plot that skill score improvements are practically everywhere, even making some headway into the Midwest up here. So that was encouraging. But the final question I think that may come up is, okay, this is still a statistical model. You may be sporting a 23.4 here, but how well does that perform compared to the Jeffs version 12, right? State-of-the-art dynamical model. So let's look at this in the sense of, okay, the statistical model probably has the most value when the NAO is amplified, or the PNA, it could be either, but we look at the NAO being amplified and we look at the same forecast initializations for the Jeffs. And unfortunately, the sample size decreased again here because the reforecasts from the Jeffs are only available once per week for week 3-4 for the past 10 years, but we have 83 in our sample size here. And for these particular initializations, when the NAO is amplified, the Jeffs forecasted with a skill score of 22.7. The merged MLR actually turned out had an identical skill score. You look at the spatial difference plots, the statistical model did considerably better in northern Alaska, probably where the trend is very important in getting the correct forecast, but it also has a significant positive component in the central plains and along the front range. So I'm not making an argument against the Jeffs or necessarily for the statistical model here, but it is interesting that they ended up with the same skill score for this particular experiment. Clearly, it's a lot less expensive to develop a statistical model. So, if you want to throw one of these things together and actually get some sense of what these climate signals mean in a linear sense, say NAO is positive right now, we're forecasting a positive NAO, what can we expect temperature-wise based on what we've observed in the past? Then a statistical model is a very cheap and inexpensive and quick way of doing that. So I think in that sense, it does add value to the forecasting process if one wants to know, and so what does it look like 3 weeks from now? NAO, what does it look like 3 weeks from now? Statistical model can quickly give us that and help us disentangle these complicated nonlinear processes that the models are able to produce. So in conclusion, by using these blocking related predictors such as the NAO and PNA, we showed that we can improve our week 3-4 statistical model, in this case, the multiple linear regression model. And much of that improvement is from hybridizing the statistical models with the dynamical models, meaning we're using the dynamical models forecast of the NAO and PNA in these statistical models, and that's how we're gaining most of our improvement. And finally, this improvement largely occurs what I would call forecast of opportunity. Statistical models likely have the most value when their predictors are amplified, and that's what we're finding in this case. So when the NAO is amplified, these forecasts of opportunity, the statistical model performs on par with the Jeffs version 12. So you may have noticed I've not mentioned anything about precipitation since the introduction slides, and that's because positive results have been elusive. But we're still doing some tests, always hold out hope. And moving forward, given these results, we are going to create an experimental tool for the week 3-4 forecaster that monitors the merged MLR's performance in real time. Ultimate goal here is at least to me, I think the ultimate goal is that we can improve our forecast for cold during winter, below normal anomalies. You know, there's a lot of variability in winter. Clearly, this is a trend, but as we've seen winter after winter for the last 10 years, you know, cold does happen. You know, it's not an impossible occurrence, but we usually miss those forecasts. Those are usually our most negative skill scores when those observations of cold do occur. So anything we can use, any sort of tool we can, you know, latch onto that can improve these forecasts of cold would be useful for the forecaster. So that wraps up my presentation. I really appreciate the opportunity to share this work. Thank you.
Great, thank you. If you take a look at the questions document, Cory, there's 3 questions on there for you. We have a few minutes if you have time to answer 1 or 2.
Sure. So the first question, were the forecasts of opportunity predicated on the sign of the amplified NAO-PNA, or did you look to see whether the skill was coming from blocking in particular? So the simple answer is yes, but I forgot what the response was. A more complicated answer is I looked at forecast for above normal and forecast for below normal and skilled both of those forecasts. And so one would obviously associate the below normal forecast with the negative NAO. So that's kind of the assumption we're making here. And there was skill score improvement with the negative NAO. Problems with that was the sample sizes were rather small, so I didn't want to share that here today. But I saw skill score improvements both with the positive NAO and the negative NAO in terms of those above or below normal forecasts if one associate the state of the NAO with those 2 states of the atmosphere. So any idea why the MLR NAO shows considerable improvement over the Southwest US, where NAO regression coefficients seem to be much lower than the Eastern US? No, that is something we've noticed ourselves and would like to look a little bit more into, because that is a great question. The regression coefficients are clearly stronger in the Eastern United States, and why it would improve in the Southwest US is not entirely clear to us yet. You showed the merged MLR has similar skill compared to Jeff's version 12 when the indices are amplified. How does the skill compare for all the cases of indices? That's a great question. The Jeff's version 12 does beat the statistical model for all cases of the indices. I would say, so I was showing around a 16 something for all cases, and the Jeffs would be around a 22 to 23 again. So the Jeff score actually didn't change much depending on the state of the NEO. So Jeffs is beating by about 40% in terms of all cases. Good question. The Jeff's version 12, was it bias corrected? No, it was not bias corrected. So no, wait, I'm sorry. No, let me take that back. I did bias correct it. I did remove its mean bias. I did that in a fair sense. I removed it using a training period that was independent of its verification period. So it was bias corrected, but it was not calibrated. And that's why I said no when I first read the question. So it was not calibrated in the sense that the probabilities being issued by the Jeffs were reliable. And there's one last question being typed in here. Do you think the state-dependent skill increase, NAO-PNA, comes from the fact that the trajectory is slowing down? And the rest of the question hasn't been typed yet. So basically a persistence. Do you think the state-dependent skill increase comes from the fact that the trajectory is slowing down, blocking snow wave, state-dependent persistence? Yes, I think there's some of that definitely going on, particularly for the NAO. So the NAO, when it's negative, right, it's blocking, it'll slow down the flow, and it also will retrograde a bit over time, and you'll see that signal actually propagate to over CONUS. PNA I'm not as sure about, because in terms of retrogression, that would actually send it further out into the Pacific. And also the PNA, I should say, is probably not entirely independent, and nor is the NAO, but not entirely independent from ENSO and the MJO, whereas the NAO definitely has some sort of intrinsic internal variability from wave breaking and whatnot. So it's more of a critter on its own. And Karen, there are a few more being typed in, but I'm not sure if you want me to wait for them to be typed or we move on.
Since we're only 2 minutes to the end, if you could just respond to the questions in the document, that would be great, Cory. Thank you.
Okay, great. Thank you.
Yep, I just want to let everybody know the next webinar will be Monday, October 4th. And our speakers are Zane Martin from CSU, who'll be discussing using simple machine learning models to predict the Madden-Julian oscillation, and John Gottschalk from CPC, talking about the CPC Global Tropics Hazard Outlook, background, current operational products, and work to transition to a probabilistic format targeting the week 2 to 3 period. So we look forward to seeing everybody next month. And if you want to see this presentation again, we will be uploading this onto our VLab website where you can check it out there or any other past webinars. So thank you, everybody, and have a great day.
Thank you, Karen.